Good afternoon, guys. Good afternoon to the first class of this week. So, today we are in the lecture 30 of fluid mechanics subject. So, in the last two classes, we have started the unit 3 where we have discussed about the introductory of laminar flows and turbulent flows, right? So, we have discussed what is the meaning of laminar flow, what is the meaning of turbulent flow, what is the meaning of transition flow, how the Reynolds experiment has done based upon the types of flows in a container by taking a dye. So the scientists have done in the year 1883 itself only how the liquid is flowing in a container through the dye, and what are the various types of flows of fluid, right? So with this, you have concluded we are having a laminar flow or a viscous flow, transition flow, and turbulent flow. And also we have discussed about the characteristics of what are the various characteristics of the laminar flow and transition flow and turbulent flow, and what are the applications of Reynolds number, సో ఇవన్నీ మనము లాస్ట్ 3 క్లాసెస్లో యూనిట్ 3 గురించి మనము చెప్పుకున్నాం. నౌ విల్ సీ what are the various derivations or what are the various analysis, what are the various types of flows in the other categories, how the velocity and shear, how the other forces are acting on the laminar flow, and what are the shear and velocity distributions of the turbulent flows, right? So by making use of the some of the scientists Hagen-Percy's formula and other Moody's chart, pipe network problems, the Hazen-Williams formula, hot cross method, we will see how the velocity, how the shear distribution takes place in the these types of laminar and turbulent flows, right? Okay. So this figure will be until the unit 3 is completed. You can see this figure only for your just inspiration or motivation, right? Nice. So in the last class we have discussed about what's the meaning of friction, right? So we are in the unit 3 with discussing with the fluids. We are discussing about the liquid friction. So apart from liquid friction, we are having other various types of friction types. We are having static, dynamic, fluid, dry friction, wet friction, lubrication friction, like this. And we have discussed the various examples of this fluid friction also. Then what are the various laws of fluid friction? So what does this law tells about the fluids, right? The first one, if you see the first one, the fluid friction occurs between fluid layers, right? The fluid friction occurs between the fluid layers that are moving relative to each other. This internal resistance to flow is named viscosity. So whenever the fluid is flowing in between the two layers, and those machines or parts are moving with each other, against each other, having some clearance, in that clearance whenever the fluid is entering it and making the material with a flow, with a easy flowing, అంటే ఒక రెండు మెటీరియల్స్ అండ్ ఆబ్జెక్ట్స్ మధ్యలో ఎప్పుడైతే ఆ రొటేటింగ్ ఆబ్జెక్ట్స్ కానీ ట్రాన్సిషన్ మూమెంట్ కానీ ఉన్నప్పుడు whenever the fluid is entering into those layers and acting as a resistance to flow, that is nothing but a viscosity, which is a property of a fluid. Next, the viscosity of a fluid is described as its thickness. So viscosity ఎలా చెప్తాము fluid కుందని, it depends upon the viscosity index, that is a thickness. Thus the water, right, the viscosity is described as its thickness, that is viscosity index. Thus the water is a thin having lower viscosity, while honey is having a thicker viscosity, which is having higher viscosity. అంతే కదా? So when you consider an example, if you take a water as example, so water ni manamu రెండు వేల మధ్యలో వాటర్ని ముట్టుకొని ఇట్లా వేళ్ళ మధ్యలో ఇట్లా జస్ట్ షేక్ చేసినప్పుడు వేళ్ళ మధ్యలో you can see some sort of friction. Ade if you take a coconut oil, finger మీద వేసుకొని డ్రాప్స్ రెండు ఫింగర్స్ పట్టుకొని మధ్యలో ఫ్రిక్షన్ లాగా చేస్తే యూ కెన్ ఫీల్ సమ్ సార్ట్ ఆఫ్ స్లిప్పరీనెస్, జారుతున్నట్టుగా ఉంటుంది. అదే ఇఫ్ యూ టేక్ ఎ హనీ, అగైన్ ఇఫ్ యూ టేక్ ఎనీ గ్రీస్, అగైన్ ఇఫ్ యూ టేక్ ఎనీ వ్యాక్స్, so you can feel some different sort of experiences when you keep in your fingers and you will rub the fingers. So then with this we can say the viscosity, it is having a thin viscosity, it is having a thick viscosity, right? Next, the less viscous the fluid, the greater its ease of deformation or movement. So what the next law is saying, ఎప్పుడైతే విస్కస్ నేచర్ is less for a fluid, వాటర్కి తక్కువ ఉందనుకోండి, ద గ్రేటర్ విల్ బి ద డిఫార్మేషన్, అంటే డిఫార్మ్ అవ్వడానికి ఎక్కువ ఛాన్సెస్ ఉంటుంది. వెన్ ఆర్ ద మెటీరియల్స్ ఆర్ రబ్బింగ్ అగైన్స్ట్ ఈచ్ అదర్, సో డ్యామేజ్ అవ్వడానికి, డిఫార్మ్ అవ్వడానికి, ఎరోడ్ అవ్వడానికి, కొరోజన్ అవ్వడానికి, మెటీరియల్ డిసిపేట్ అవ్వడానికి, అరిగిపోవడానికి యూ హ్యావ్ ఎ ఛాన్స్. దట్ ఈస్ ఆల్సో వన్ లా. సో ఆల్ ద రియల్ ఫ్లూయిడ్స్ ఎక్సెప్ట్ ద సూపర్ ఫ్లూయిడ్స్ కాకుండా all the real fluids offer some sort of resistance to shearing and therefore are viscous and therefore are called viscous. So majority all fluids are having some sort of viscous nature. Depends upon those viscous nature, the forces will be acting on the objects. So the laws of the fluid friction says that there will be some sort of internal resistance whenever the flow is occurring in between the two materials, not as nothing but a viscosity. The viscosity of a fluid is decreased by the thickness. So other law and it is described by the thickness. So if you take an example of water, honey, grease or oil, you are having different sorts of viscosity. So the next law is whenever the fluid is having less viscous nature, automatically the objects are of greater deformation. Next, all real fluids offer some resistance of shearance and therefore are called viscous or laminar. So these are the laws of fluid friction, what we'll discuss in the fluid friction laws. Next, so if you see the pipe flow theory, so various scientists have been discussed about the pipe theory. Various scientists have been discussed about the pipe flow theory. So whenever the fluid is passing in the pipes in different channels, bend, T bend, U bend, cross section or some other different diameters of pipes from lower diameter to higher diameter, lower diameter, what happens, there will be some sort of changes in the discharge, velocity, shear forces will acting on it. So based on that, many of the scientists have given some sort of explanation. So here in this unit, you are having some scientists gave some of the theories. In that, the first one, in the year 1840, the Hagen and Pesely had contributed some sort of theories for this laminar flow equation gurinchi. Hagen Pesely has given some sort of theory explanation about the how the laminar flow occurs in the liquid, and based upon the some assumptions and based upon some derivations, he given some formulas. We see in the next one, there is an 1850, in the year 1850, the Darcy and Weisbach. So these are the names, these are the name of the scientist, Darcy and Weisbach. They had given some sort of explanation about the turbulent flow equation. So the laminar flow is said by the Hagen and Pesely, whereas the turbulent flow was explained by Darcy and Weisbach. Next, the year 1883, the scientist Reynolds had distinguished between what is the laminar flow ante enti, turbulent flow ante enti, ఒక experiment ద్వారా in the year 1883 Reynolds has experimented and gave the distinction between the laminar flow and turbulent flow. Next, in the year 1913, Blasius, the scientist Blasius, the doctor, the person Blasius have given the contribution about the friction factor equation or smooth pipes. The friction factor equation gurinchi Mr. Dr. Professor Blasius has given some sort of explanation and contribution. Next, in the year 1914, Stanton and Panel. In the year 1914, Stanton and Panel experimental values of friction factor for smooth pipes. He had contributed some sort of values for the smooth flow of the pipes. Next, Nicotides. He is a scientist. He was a scientist who has made some experimental values for the friction factor for the artificially rough pipes. Smooth pipes gurinchi, Stanton and Panel has given some sort of explanation, whereas for the artificially rough pipes gurinchi, friction factor తెలుసుకోవడానికి the scientist Nicotides has made some assumptions and contribution. Next, in the year 1930, Trandel and von Karman has gave the contributions about the equations for rough and smooth friction factors. So whatever the scientist in the year 1914 లో 1913 లో జరిపిన experiments లో smooth pipes ki rough pipes ki whatever the friction factor values they have given, so the scientist Trandel and von Karman has made the experimenters in between both rough and smooth friction factor, right? Next, in the year 1937, Holbrook and White made some of the contributions for the friction factor for commercial pipes and transition formula. Next, in the year 1944, Moody chart antam, the Moody diagram for commercial pipes. So Moody was contributed. Moody studied about the commercial pipes and transition formulas made by Holbrook and White, and he made a Moody chart. So based upon the Moody chart, so for the commercial pipes, so we have to see the any calculations or values or equations based upon the explanation. We have to see the Moody chart. Next, in the year 1958, Akers. In the year 1958, Dr. Akers made some assumptions on hydraulic research station charts and tables for design of pipes and channels. So design of pipes and channels gurinchi Dr. Akers has made some sort of research and made some design of pipes and channels. Next, in the year 1975, Barr, solution of the Colebrook-White equation. He made some equations about the design of pipes and channel. So like this, the various scientists have contributed some sort of information about the pipe flow theory for the fluids. So in this unit, you are having only very few of the scientists and their derivations, like Hagen-Poiseuille. So what we'll discuss in this unit is about the laminar flow equation, about the turbulent flow equation, about the distinction between laminar flow and turbulent flow, right? And we'll discuss about the equations for rough and smooth friction factors. We'll discuss about the Moody chart, right? We'll discuss about the Moody chart. So like this, we are having some sort of discussions in this unit 3, right? Only 1%. Next one. Now we'll see. 1 second. Yeah. Next topic is laminar flow in the pipes. The next topic. So we'll discuss the laminar flows in the pipe. We'll discuss turbulent flows in the pipe. So we'll discuss open pipes and closed pipes also, right? Laminar flow ni manamu inkoka rakanga cheppalante we'll call them as viscous flow. We'll call laminar flow as viscous flow. Okay na? Next. So in this laminar flow pipes, so we will consider a pipe and we'll do some of the calculations based upon the laminar flow conditions. Now we consider a steady, a laminar and incompressible flow of fluid with constant properties in the fully developed region of a straight circular pipe. So we are taking a straight circular pipe. So we are taking a straight circular pipe where where the fluid is having constant properties. The properties గురించి మనం యూనిట్ 1 లో డిస్కస్ చేసుకున్నాము. We are having the constant properties of the fluid where it is moving steadily, where it is moving with the incompressible and laminar type of flow, right? Next point. In fully developed laminar flow, full గా డెవలప్ చేసిన laminar flow లో each fluid particle moves, each fluid particles moves at a constant axial velocity. So it will move at a constant axial velocity along a streamline, and the velocity mu r remains unchanged in the flow direction. So what happens in the fully developed laminar flow? Fully developed laminar flow అని ఎలా చెప్తాము? Whenever the fluid is having whenever the fluid is having the properties which are constant, చేంజ్ అవ్వకుండా ఎప్పుడైతే ప్రాపర్టీస్ కాన్స్టెంట్ గా ఉన్నాయో and it is moving in a straight circular pipe, we are calling them as a fully developed laminar flow. Next, each fluid particle, okay, each fluid particle moves at a constant axial velocity. Each fluid particle moves at a constant axial velocity along a stream pipeline, and the velocity profile mu r remains unchanged in a fluid flow direction. There is no motion in a radial direction. So manaki radial direction lo move adaniki chance ledu. Why? Because it's a straight pipe, and thus the velocity component, the direction normal to the pipe axis, is everywhere zero. So therefore the velocity component in the direction normal to the pipe is zero. Why? Because it's a straight pipe. There is no acceleration since the flow is steady and fully developed. So assumptions lo there is no acceleration. There is no acceleration for the flow. Why? Because the flow is very steady, laminar and incompressible and fully developed flow. So based on this one, we'll do a small experiment how the flow is going. So we have considered a cylindrical pipe of some diameter where the pipe is straight. So మనకి ఇది చూసారా, ఇది క్రాస్ సెక్షన్ అన్నమాట. ఇది ఈ పైప్ ఒక థిక్నెస్, ఒక పైప్ని తీసుకొని మీరు అడ్డంగా కోసారనుకోండి, సో మనకి ఇది క్రాస్ సెక్షన్ లాగా అనిపిస్తుంది, పైప్ క్రాస్ సెక్షన్. Now here the water is flowing in a unidirection, uniformly, steadily. Okay, so now we see a free body diagram of a ring shaped differential fluid element of radius r. Radius r, okay, so ఇక్కడ నుంచి సెంటర్ నుంచి ఇది రేడియస్ అంతే కదా, this is the internal radius r, radius r, thickness dr, the thickness ఇది, the thickness is dr, and the length dx oriented coaxially with the horizontal pipe in a fully developed laminar flow. So ఇది దీన్ని ఈ చిన్నదాన్ని ఎగ్జాగరేట్ చేస్తే వీఆర్ కన్సిడరింగ్, ఇక్కడ ఏం చెప్పాడు, వీఆర్ కన్సిడరింగ్ ఏ profile, we are considering a small profile, constant axial velocity along a streamline with the profile remains unchanged. So we are considering a fluid particle. So ఇది fluid అనుకుంటే, ఈ ఆరెంజ్ కలర్ లో ఉన్నది మొత్తం fluid అనుకుంటే, in that fluid we are assuming a fluid particle like this. So top view, front view, ఏదో ఒకటి. So this is a dr, this is a dx, right? This is the views. dr వచ్చేసి ఇది, dx వచ్చేసి the length. So here the water is flowing uniformly. So the maximum Umax at the direction Umax at the center. So the Ux is the x-axis direction. So the smaller the bigger. The change in the radius. Change in the radius. Now, so exaggerating this one. So the direction of flow is in this direction. So we are taking the pressure P. Now P of next direction, right? P next direction, the resistance from this side, that is P of x plus dx, P of x plus dx. Now the tau, the value of r, the radius, tau r in this direction, it is tau r plus dr, tau r plus dr. So taking this small fluid element as an example, we will make an equation that is 2 pi r, because it is circular pipe, you are taking the circumference of the pipe, that is 2 pi r dr p in x direction minus 2 pi r dr p x plus dx. సో ఈ x plus dx నుంచి దీన్ని మైనస్ చేయండి, r plus dr నుంచి r ని మైనస్ చేయండి. therefore 2 pi r dr p x with respect to x minus 2 pi r dr p x plus dx. Okay, we are adding, so plus 2 pi r dx tau r minus 2 pi r dx tau r plus dr. So that is equals to 0. Now after getting this one, after getting this equal, so after getting similar values, so taking one side, so we are taking one side, we are cancelling 2 pi r in all the cases. Now we are making this simplified, this equation will be simplified, r of p of x plus dx minus px by dx plus r tau r plus dr by dr minus r tau r plus dr minus r tau r by dr is equals to 0, right? Is equals to 0. Right? So after simplifying this one, we'll get this equation. So after getting this equation, again you are making a simplification, that is r with respect to dp by dx, r of dp by dx plus d r tau by dr is equals to 0, where tau is equals to minus mu du by mu r. Tau is equals to minus mu du by dr, that is equals to mu by r d by dr common into r du by dr is equals to dp by dx. Got it? Next. So after getting this one, dp by dx, the dp by dx is equals to minus 2 tau w by r, minus 2 tau w by r, minus 2 tau w by r. Next. So mu r, so we are taking this one, the same figure we are taking this one. So the in x direction, that is in r, that is the radius r, right? So we are exacting this one, we are getting pi r square p plus dx is equals to 2 pi r dx tau w. Therefore u of r is equals to r square by 4 mu this dp by dx plus c1 radius, inner radius plus c1 inner radius plus c2. Therefore dou u by dou r, so దీన్ని differentiate చేస్తే dou u by dou r is equals to 0 at r is equals to 0, right? Therefore u is equals to 0 and r is equals to bigger. Therefore substituting this here, ur is equals to minus r place lo substitute this r is equals to r square by 4 mu into dp by dx, so into 1 minus r square by capital R square, right? Therefore this is the average velocity, therefore so differentiating v average is equals to 2 by r square, differentiating with respect to r, ur r dr is equals to minus 2 by r square, with respect to r square by 4 mu dp by dx into, so just e value you can substitute change, this value substitute here. Okay, then that is equals to, in differentiate చేసిన తర్వాత you are getting that is equals to r square minus r square minus by 8 mu dp by dx. Okay, now we have to find the velocity profile. For that, mu var is equals to 2 average bracket lo 1 minus r square by r capital R square, close the brackets. There is a velocity profile. So the maximum velocity at the center line, Therefore, U max is equals to 2 times the average. 2 times the average. That is force balance pi r square P minus pi r square P plus dP minus 2 pi r dx tau W is equal to 0. Simplifying, dP by dx is equals to 2 Tw by R. So E 2 T BW 2 T tau by R మనం ఇక్కడ substitute చేసాం, right? So that's why UR is equals to the velocity profile is 2. So keep this formula in mind. So whenever you ask for maximum velocity center line, therefore U max is equals to 2 V average, right? Next, what happens to the pressure drop and the head loss? So when you take a circular pipe, what happened to the pressure drop and the head loss? A quantity of interest in analysis of pipe flow is a pressure drop, that is change in the pressure delta P. Since it is directly related to the power requirements of the fan or a pump to maintain the flow, we note that dP by dx is equal to constant, and integrating x is equal to x1, where the pressure P1 to P1 to x is equals to x1 plus L, sorry, x1 plus L, where P is pressure 2. Therefore, based upon this pressure drop, dP by dx is equals to change in the pressure under delta P. Therefore, P2 minus P1 by the length of the pipe L. Therefore, the laminar flow delta P is equals to P1 minus Pt P2. That implies that is equals to, so 8 mu L V average by R square, that is equals to 32 mu L V average by D square. Okay, so the laminar flow profile change in the production of pressure is equals to, this is a formula. A pressure drop due to the viscous effects represents an irreversible pressure loss, and it is called a pressure loss, that is delta PL. Therefore, the delta PL is equals to F into L by D rho V square average by 2. Therefore, the pressure loss for all types of fully developed internal flows. Okay, so rho V square average by 2. There's a dynamic pressure. So the reactive friction factor F is equals to 8 tau W by rho V square average. That is a Dachy friction factor. So for a circular pipe with laminar, F value is equals to 64 mu by rho D V average. That is equal to 64 by Reynolds number. So this is Reynolds number kada. This mu by rho dV is equals to Reynolds number kabatti 64 by Re. Therefore, what is the head loss here? Head loss HL is equals to delta PL, change in the pressure divided by rho into G. So delta PL substitute cheste, that is FDLD by V square average by 2G. So ikkada undi kada delta PL, substitute this delta PL at the friction head loss, that is equals to delta PL E values into rho G. So in the laminar flows, the friction factor is a function of the laminar flows. In the laminar flow, the friction factor means the function of Reynolds number only, and it is independent of the roundness of the pipe surface. The head loss represents the additional height of that fluid needs to be raised by the pump in order to overcome the friction loss in the pipe. 1 second. Right? Next. So with this, we got the head loss of the laminar flow. Now, if you see in the horizontal pipe, for W with respect to pump, so these are the additional things for W with respect to the length B into delta PL, that is equals to volume rho G HL head loss, that is equals to mass G into head loss. Therefore, V average is equals to so P1 minus P2 R square by 8 mu L, that is equals to P1 minus P2 R ni diameter lo cheskunte diameter square D square by 32 mu L, that is equals to P1 minus P2 means delta P, so delta P into D square by 32 mu L. This is a horizontal pipe formula. So if you see the Poiseuille's law, V volume is equals to V average, velocity average into AC. That implies P1 minus P2, V average is equals to enter P1 minus P2 R square by 8 mu L, A area pi R square. Together, V average volume is equals to V average into area. Therefore, velocity and T, this is the formula for velocity, and area is equals to pi R square. So, దీన్ని ఇంకొంచెం simplify చేస్తే we will get P1 minus P2 or pi d square by, right, this one, or pi d square by 128 mu L, that is equals to, so radius ni diameters to convert cheste this thing you are getting. Then P1 minus P2 and delta P kabatti pi d square by 128 mu L. Got it? See here, you can also see these formulas. So the head loss delta PL is equals to F of LD by rho V square average by 2. Head loss HL is equals to delta PL by rho G. So just in the substitute cheste, you will get the head loss, right? So whenever you are taking a pipe for a specified flow rate, the pressure drop and thus the required pumping power is proportional to the length of the pipe and the viscosity of the fluid, but it is inversely proportional to the fourth power of the diameter of the pipe. Therefore, the diameter of the pipe D, capital D, so for the pump is 16 horsepower with the average flow velocity. When the pump is having 1 HP with the diameter of 2D, then it is divided by 4 times, right? 4 times. Okay. The relation for the pressure loss on the head or the head loss is one of the most general relations in the fluid mechanics, and it is valid for the laminar or turbulent flows, circular or non-circular flows, and a pipe with a smooth or rough flows. The pumping power required for the laminar flow piping system can be reduced by a factor of 16 by doubling the pipe diameter. Got it? Next. The pressure drop delta P equals to the pressure loss delta PL. In the case of horizontal pipe that is one case. If it is in the vertical pipe, it is in the one case. So for a horizontal pipe, the delta P is equals to the pressure of head loss delta PL. But this is not the case for inclined pipes or pipes with variable cross-section area. So the delta P is equals to delta PL annar when in case of horizontal pipe. But the pipe thickness vary avutundi, the pipe cross section varies and the pipe is inclined pipe, so this will not be considered. Okay, next, this can be demonstrated by writing an energy equation study. So the delta P is equals to delta PL only in case of horizontal pipe, but delta P is not equal to delta PL in case of inclined pipes and variable cross section area ni. So if you demonstrate by taking energy equation concept, right, by using one dimensional flow, we can write this one as pressure energy plus kinetic energy plus datum line and చెప్పొచ్చు, right? So what is the pressure energy? P1 by rho G plus alpha 1 V1 square by 2G, the kinetic energy, plus datum energy Z1 plus horizontal pipe lo pump. So H pump mu is equals to P2 by rho G plus alpha 2 V2 square by 2G plus Z2 plus H turbine E plus head loss. So ఇప్పుడు దీన్ని మనము కామన్ తీసుకుంటే P1 minus P2 is equals to rho of alpha 2 V2 square minus alpha 1 V1 square by 2 plus rho G Z2 minus Z1 plus H turbine E minus H pump U plus HL. So ఈ పైన ఉన్న మనము energy equation ని we can write in this fashion. Therefore, the pressure drop delta P is equals to P1 minus P2, and the pressure loss delta PL is equals to rho into G into HL for a given flow section or equivalent. So the flow section is equivalent so that there are no hydrostatic or gravity effects. That is, Z1 is equals to Z2. Second, the flow section does not involve any work devices such as a pump or a turbine, since they are not, there is no change in the fluid pressure. If there is no change in the fluid pressure, the devices what we are using as a pump or a turbine does not involve any change. Therefore, pump head is equals to pump turbine is equals to 0. What next? What is the third point? The cross section area of the flow section is constant. The cross section is constant kabatti. Therefore, the average flow velocity is also constant. Therefore, V1 is equals to V2. And what is the fourth point? The velocity profiles at section 1 and 2 are same. What are the velocity profiles at section 1 and 2? Because the cross section is constant, the velocity profiles are also same. That is, alpha 1 is equals to alpha 2. Next. So till now we have got about the pressure difference gurinchi formulas తీసుకున్నాం, and also the velocity gurinchi formulas తీసుకున్నాము, and also the change in the pressure also we have took the thing, and also we have got the head loss formulas, right? So based upon these formulas we will have some problems. Very easy to solve the problems, don't get worried, right? So మీకు దీంట్లో వస్తే క్వశ్చన్ explain or derive the Poiseuille's formula గానీ లేదంటే derive the laminar flow in a horizontal cross sectional pipe అని క్వశ్చన్ రావచ్చు. ఓకే, నెక్స్ట్ ద ఎఫెక్ట్ ఆఫ్ గ్రావిటీ ఆన్ వెలాసిటీ. ఎఫెక్ట్ ఆఫ్ గ్రావిటీ ఎలా ఉంటుంది ఆన్ వెలాసిటీ అండ్ ఫ్లో రేట్ ఇన్ laminar pipe. So laminar flows లో what will be the effect of gravity on a velocity and the flow rate? So if you see the free body diagram of a ring shaped differential fluid element of radius r, thickness dr, and the length dx, oriented coaxially with the inclined pipe in a fully developed laminar flow. Now see the figure. If you are taking inclined developed pipe, inclined fully developed pipe, so this is the x-axis, this is the y-axis. So inclined kabatti ee base ki it is making an angle theta. Therefore, the same mundu meer తీసుకున్నట్టుగా you take a small particle of a fluid, that is dr and dx dimensions. So making the x-axis and this is y-axis. So you are making a body diagram. So thereby the weight is acting perpendicularly downwards. Therefore the theta will be, therefore the angle will be the theta, right? Next, the px is moving in this direction. Px plus dx change in direction is moving in this direction. The tau r is in this direction. Tau r plus dr is in direction. Okay, na? First the figure వేసుకున్న తర్వాత then we'll see the things. So the weight in respect to x direction, wx is equals to w sin theta, that is equals to rho g v element sin theta. W is equals to rho g into v sin theta. That implies rho g, right? So 2 pi r dx, 2 pi r dx the bracket sin theta. So ఇప్పుడు దీన్ని మనం సింప్లిఫై చేస్తే 2 pi r dr, 2 pi r dr into pressure x. So దీన్ని same 2 pi r dr pressure with x minus 2 pi r dr p x plus dx plus 2 pi r dx tau r minus 2 pi r dx tau r plus dr minus r ఇది రాసేసాను అంతే, minus rho g 2 pi r dr dx sin theta is equals to 0. So ఈ ఈక్వేషన్ మీరు ముందు చేసిందే. So whenever you are having a circular pipe, so this is the thing you have written, right? So the same thing right for here also. Here now after simplifying this one, you are getting mu by r dr, that is equals to this one. After further simplifying, mu r is equals to this one. Therefore the velocity, average velocity is equals to delta p minus rho gl sin theta divided by 32 mu l, where it is converting into d square. The volume is equal to delta p minus rho gl sin theta pi d cube by 128 mu l. So here the time is also completed. We'll discuss the class in the next lecture. So thanks for listening. Once the video is completed, I will upload in the YouTube. Later this link will be added to your group. Okay, thanks for listening. Have a nice day. So I will explain this derivation once again, don't worry.